Okay, so in the last video we talked about optimization and applications, essentially different things we can use the first derivative to solve. For the last section it was optimization and using the first derivative to find maximums and minimums. Now we're going to look at another application of a derivative, but we're actually going to base it on something that we've done before. Again, as I've said before, we'll start by looking at problems we already know the answer to, so then when we kind of see the trick and how it works, we'll understand that our answer is correct, and then we can expand on it and use it for problems we don't know the answer to. So we're going to go back to the beginning of the class and talk about limits. And suppose I have the limit as x approaches 1 of x squared minus 1 over x minus 1, which, because I use a lot of the same problems, I'm sure we actually already solved this one. And we know if I plug in the 1, I get 1 squared, 1 minus 1, which is 0, over 1 minus 1, which is 0. And the terminology for this is actually called an indeterminate form. There's a lot of different indeterminate forms in math. We're going to look at several of them in this video and the next few videos. But that's an indeterminate form, and essentially the problem is I don't know what 0 over 0 is, and it can actually be a lot of different things. And we needed to find a way to find that limit. And if you recall, the trick is actually just do algebra. So in this case, we factored the top and bottom. Now those cancel, and I end up getting the limit as x approaches 1. With those canceled, it's just x plus 1. Now I can plug in 1, and I get 2, and there's my limit. And we certainly know that you could just graph this and you'd see this is a removable discontinuity in the terminology of, say, 171 pre-calc. And it's essentially the graph of a line with a hole in it where it's undefined at 1, limit from the left, limit from the right is 2. We actually did, like I said, a lot of this graphically and algebraically at the start of the semester. And another one we actually looked at was the limit as x approaches 0 of sine x over x. And the problem is, again, if you plug in there, you get sine of 0, which is 0, over 0, which is indeterminate. And that one's actually solvable. You can do some algebra and some geometry and trig, and you can get the answer. But if you recall, if you look in your notes, we actually said, I do believe, and we're going to test this, that the limit there is equal to 1. But then, of course, I mean, I can have lots of really fun type problems. The limit as x approaches 0 of x ln x. Well, if I plug in there, as x approaches 0, that becomes 0. ln of 0, it's undefined there, but if you think about the graph of ln looks like this. As x approaches 0, this approaches negative infinity. And then what in the world is 0 times negative infinity? You would assume it's 0. It may be, it may not be. But this is another indeterminate form. Lots of things involving zeros and infinities end up giving me indeterminate forms in math. And the problem is, these are pretty simple and straightforward. Some we can solve with algebra. Some would require a little bit more algebra. So I actually have no idea how to solve this one algebraically. So we need a new trick to start solving problems like this and a lot more complex ones. And I'm going to leave that problem up there because we're going to solve it again using this new trick. And the trick is called L'Hopital's rule. Or as a lot of people say, L'Hospital, but there's no S there, it's just L'Hopital, it's the guy's name. But anyway, L'Hopital's rule. And let's see. If f of x and g of x are continuous on the open interval AB, and the limit as x approaches c of f of x equals the limit as x approaches c of g of x equals 0, then the limit as x approaches c of f of x over g of x, which in this case would just be the limit as x approaches c of f of x over g of x, which would be 0 over 0, which is indeterminate, like this. then L'Hopital's rule says this is equal to the limit as x approaches c of f prime of x over g prime of x. Understand when you see this, this is not saying, if I have something like this, this is a rational function, this is my f of x, right up here, this is my g of x, and clearly the limit as x approaches c of f of x is 0, the limit as x approaches c of g of x is 0, so I get 0 over 0. According to L'Hopital's rule, to find that limit, I can take the derivative of f, the derivative of g, and then take the limit again and see what I get. The problem is, just the one issue that can occasionally arise with this is not a quotient rule. That does not mean I take this rational function and I do the derivative quotient rule. Bottom derivative top, top derivative bottom, over bottom squared, blah, blah, blah. This is saying I treat it as two separate functions and I find the derivative of the top and I find the derivative of the bottom separately, and then I rewrite my new fraction and I apply the limit again. And it's also a requirement that this limit must exist. So L'Hopital's rule won't work if this limit doesn't exist right here. But as long as it does, then this gives me a simple way to find the limit. To see if it works, to see the idea. Up here, we want to find the limit as x approaches 1 of x squared minus 1 over x minus 1. And I will point out, on say your homework and all of that, and even on your exam, show your work, because in order to apply L'Hopital's rule, you have to make sure you meet the conditions of L'Hopital's rule. Meaning, I have my two functions. If I take the limit, I get 0 over 0. That's indeterminate. Now I can apply L'Hopital. I take the derivative of the top. The derivative of x squared minus 1 is 2x. The derivative of the bottom. The derivative of x minus 1 is 1. Now I take the limit. The limit as x approaches 1 of 2x. Plug in the 1 and you get 2. Which is exactly what we got when we did this algebraically. Which means we can kind of see that this trick is working. There is a proof of L'Hopital's rule. It's actually only like 3 lines long. I don't want to take the time to do it. It's in your book. And it's actually not all that challenging. You just write the definition of the derivative, do one algebraic step of cancellation, and you're done. So it's not worth wasting time here doing. But now this trick clearly seems to work, so we can test it again. Suppose we have the limit as x approaches 0 of sine x over x. If I plug in 0, I get sine of 0, 0 over 0. Now I apply L'Hopital. The derivative of sine is cosine x. The derivative of x is 1. Now I take my limit as x approaches 0 of cos x over 1, which is just cos x. If I plug in 0, cos of 0 is 1. I get 1 over 1, which is 1. Which is exactly what we said we should get. I actually pointed out earlier when we did this limit that there are algebraic and trigonometric ways to do it, but there were other tricks we'd see later in the semester that make it easier. L'Hopital right here. It makes a lot of this stuff easier. Derivative, derivative, done. 2 steps. So it's easier than a longer limit definition, which is why I didn't really go over it when we went over the limits the first time for this one, because this method is easier. But there's a lot that can kind of pop up as we deal with these limits. Suppose we have this. The one we were talking about, the limit as x approaches 0 from the positive, because it's undefined on the left, of x ln x. And the problem is, we already said that limit is equal to 0 times negative infinity. That is indeterminate. 0 times infinity, or negative infinity, is an indeterminate form in math, but we can't apply L'Hopital. L'Hopital only works if I have 0 over 0. But if I can somehow rewrite this so that it's indeterminate in this form, then I can apply L'Hopital, and then I'll be good to go. So, there are different algebraic tricks you learn. This is another standard one that we use a lot, and this is like the first time you get to see it, so jot it down. A lot of times what we do is, if I need to write this as a fraction, x is the same as 1 over x in the denominator. Rules of fractions, this fraction right here, the x would come to the top because it's the denominator in the denominator, and it would be x ln x. So this is the same as that. I'm just using a little trick, and I'm flipping the x on the top to 1 over x in the bottom. That's a standard trick, and it pops up a lot. If you want to apply L'Hopital, and you don't have an indeterminate form like this, see if there's an x floating around, if it's a product, that you can flip into the denominator. It's a standard trick. Now, if I take the limit as x approaches 0, well, let's see. As x approaches 0, I get ln of 0. We already said that as using the graph of ln, as x approaches 0 from the positive, it approaches negative infinity. So this is negative infinity over here. This takes a little bit of intuition, but as x approaches 0, x gets smaller. As x gets smaller, 1 over x gets bigger. If this was 1 over a tenth, the 10 would come to the top, it'd be 10. If this was 1 over a hundredth, the hundredth come to the top, it becomes 100. So the smaller x gets, the bigger 1 over x gets, which means this approaches infinity. And now I have negative infinity over infinity, which is another indeterminate form. It's not the same as this one, but as it turns out, L'Hopital's rule can be extended slightly. It will work for 0 over 0 or infinity over infinity. The negative sign doesn't matter. So any form of infinity, positive or negative. These are kind of the only two conditions on L'Hopital. Has to be 0 over 0 or infinity over infinity. So now I'm going to apply L'Hopital here. The derivative of ln of x is 1 over x. The derivative of 1 over x, I'm going to assume all of you can do that really quickly. If not, feel free to use your rules and jot it down. It's negative 1 over x squared. Now, algebra, there's a negative. This x squared comes to the top, the x goes to the bottom, and I get x squared over x, which is negative x. Now, I can apply the limit as x approaches 0 from the positive of negative x, and I get negative 0, which is, of course, 0. And again, this may seem like a little bit of work. Oh, do this bizarre algebra trick, then take my derivatives, make sure I do that one correct, plug in and simplify. But the alternative is, I have absolutely no idea how I would algebraically justify that that has to be 0. So this L'Hopital is really good. I'm going to make another video, because we're almost out of time on this one, going through a lot more examples, because there are a lot more indeterminate forms and kind of algebraic tricks, some that we've seen before, some that we haven't, that we can use to solve more and more complex problems out and find limits using this L'Hopital trick.